Welcome from all over the world, and welcome to those of you online as well. Now, there have been some housekeeping notes given, but now to welcome you to this session, Missions and Mission Planning. We're going to give you presentations on the latest missions and mission concepts for prospection and sample return from the Moon and Mars, ISRU demonstrations and pilot plans. This session is actually going to be chaired by Abigail Calzada-Diaz, who is a lunar geologist. I'm sure many of you know her, and she works in identification and characterization of lunar resources on Research and Technology Associate as a Research and Technology Associate at ESRU, based here in Luxembourg. So please welcome Abigail to the stage.
Thank you, Lisa. Good morning, everybody. Welcome to the session of Mission and Mission Planning. So we have 9 talks this morning. It's a quite packed morning. Unfortunately, we don't have time for Q&A, but don't forget that you can submit your questions online to the platform, and an expert will answer to them. And also, you can approach the person directly during our networking events. So I don't want to take much time because we're already running out of time. So I'm going to welcome the first speaker in the morning, that is Matt Cross for Mission Control, and he's going to talk about how to use autonomous lunar rovers to prospect and mining the surface. Thank you.
Hi, good morning. So I am Matt Cross, and I am from Mission Control. And so Mission Control is a company based in Ottawa in Canada, and we recently celebrated our 8th birthday. And we're primarily a software-focused company, and we believe in developing software for Earth, Moon, and Mars. And our real goal and mission statement is to innovate to make advanced software viable for use in space. We're pretty excited that we do have some confirmed mission contributions. We currently have one of our AI demos uploaded and waiting execution on ESA-OPSAT. And we also have our AI terrain classifier demonstration set to land on the Moon next week. And alongside that, we will be demonstrating our operations software platform in support of that demonstration. So one of our 2 core software products is our operations software suite, Spacefarer. And this came out of some internal development where we had been conducting numerous analog operations with robotics hardware, remotely operating robots in analog environments and conducting mission operations. And we identified a real pressing need to have good operations software. As we have a reasonable extensive experience conducting science operations, and there was a lack of real user-friendly operations software out there. So through our own development, we recognize this need, and we're advancing the software, and we sort of realized that others out there would have a need for software similar to this. So Spacefarer is our core product line for supporting mission operations, specifically robotic operations, targeting rovers, but also we're extending it out into robotic arm operations as well. And then similarly, we are an AI-focused company as well, and so our second product line is Spacefarer AI, and it is a development pipeline for taking user needs through data right through modeling and deployment. We had very similarly internal development projects where we had to deploy AI models onto various different hardware platforms, including spaceflight computers. And so it's one thing to develop a model and deploy it on your local PC or some development board. It's another to be able to take that same model or even adapt that model and deploy it onto flight hardware with much different power constraints and computational capability. So we developed this development tool chain for our own internal use, and then realized that this is probably going to be a very common problem that other users will be facing as AI becomes more applicable in the space domain. And so looking at our two core product lines, we're able to look at what types of capabilities can we, and problems and challenges can we solve with these capabilities. And so when we look at lunar prospecting, lunar rovers, other types of lunar missions, what are some of the challenges that mission operators will face? So one of the core challenges that we believe will be experienced will be understanding the lunar surface to help inform mission operations. And so what are the hazard conditions and what are the terrain conditions in which the user will be attempting to operate their robotic platform? How do you map and provide geologic context within that environment in which you're operating? And then, can you better inform how to target instruments for conducting specific prospecting and investigations? So when looking at the various capabilities that we're able to contribute, we really focus in on autonomous perception. And what this enables is, for example, obstacle prediction. So identifying, what is an obstacle, what is not an obstacle. Slip and energy prediction. If you can identify and classify the type of terrain, this helps to better predict and model slip and energy consumption. Regolith is going to have different traction properties compared to, say, like bedrock. And also being able to identify specific targets of interest, help the user then be able to target their science of prospecting instruments. And then this further goes into being able to predict obstacles, identify slip and hazard conditions. This helps with traverse planning. And then being able to identify targets of interest, then this feature goes into be able to autonomously target science instruments. And then as the robotic system is able to generate data and gather data in its prospecting mission, then being able to readily identify the different types of features within the data sets then helps to better manage the data and then actually prioritize data downlink over constrained bandwidths. So one of our core and key outputs from our Spacefarer AI development pipeline is MoonNet. And so MoonNet will be our demonstration that will be operating when ispace lands next week. And so we, as far as we are aware, this will be the first demonstration of deep learning AI in deep space. As noted, there are a number of challenges in deploying deep learning models to spaceflight computers, and so this is one of the our key demonstrations is really showing that these models can be deployed and operated on spaceflight computing. So our MoonNet model was developed internally in our own moon yard. So we have thousands of images collected from our indoor moon yard. All that data was labeled and went through a training system. But we specifically targeted classes that would be relevant to the lunar surface during operations, but within a sufficiently or usable number of classes that allowed for a smaller model that could be run on spaceflight computing. So we have, based on this MoonNet model, we have a set of classes that will be used to segment the features captured from rover images. And so here we have examples of what this looks like from images taken from our moon yard. The MoonNet model that we are deploying on the surface is based on and trained with our internal moon yard imagery. Now, obviously, the moon looks very different, and part of our MoonNet experiment will be identifying how to best incorporate new mission data to update the model and perform a real-time model update during the demonstration. So when you have this capability, what does this unlock for potential users, specifically looking at lunar prospecting missions? So as an example, if your robotic system can capture an image and then identify features within that image, this helps to better, for example, autonomously target those features. So if you can identify what is a crater within the image, having some context and understanding that a crater may be permanently shadowed, and you may be looking for certain volatiles within that crater, you may want to target a thermal imager for better characterizing the volatiles within the permanently shadowed region. Whereas if you can identify rocks, you may be more interested in the mineralogy of that feature and can use that for automatically targeting either spectral imagers or a LIBS instrument or similar. Another use case that we've been looking at and demonstrating is downlink prioritization. So there could be cases where the robotic system is able to capture more data than the communication pipeline can support. And so if you're able to better identify and classify features within the image, you can then prioritize those data that are of keen interest to the end user. So in this case, capturing many images from the surface, and there's many different types of features within these images. There may be a use case in which, for example, rocks are prioritized over craters. And then those images then get downlinked and prioritized and sent to the end user. And then another example for how this can be used for supporting users is operations support for science teams. So one thing that we work with a lot and study a lot with at Mission Control is user experience and how to reduce cognitive loading for science operators during missions. And so by enabling pre-annotated images, this helps to reduce the cognitive loading on the end science user, so that they can focus on completing their science tasks and identification. By enabling pre-image annotations, they can have common conversations with other members of their users and teams. You can then, for example, query a catalog of specific features. So if you're looking at different types of rocks, like anorthosite or basalts on the surface, by having pre-annotated and identified images, you can then call up catalogs to support that. But this all sort of comes to the demonstration that we're pretty excited about. So next week, again, when ispace lands on the surface, we'll be conducting our lunar capability demonstration. So this is in collaboration with the Mohammed bin Rashid Space Center and the Emirates lunar mission. So our MoonNet payload is on the ispace lander, but it of course requires images in order to classify and segment. So the Emirates lunar rover will be capturing images, and then as those images are downlinked to Earth-based operators, those images will be classified by MoonNet on the lander, and then we will get those data products on the surface. The additional, so the added step to this experiment and demonstration is with all the raw data and imagery coming from the rover, we'll be using that to then reclassify those images, retrain the model, and then perform a model uplink and update in flight. And so this will be a demonstration of not only of a deep learning model in flight, but also updating that model based on a limited new data set. So we're pretty excited about this capability demonstration. We do thank the Canadian Space Agency for their contribution to enabling this. And then something else that we like at Mission Control is inspiring the next generation of explorers. So we use our Spacefarer platform to to enable students from around the world to conduct analog operations operating our rover system in our indoor moon yard, and it gives them the opportunity to experience and understand how remote operations are conducted and really get them excited about space. And so just in summary, we're pretty excited about our upcoming demonstration next week when ispace lands on the moon. And if you're interested in learning more about Spacefair and Spacefair AI, I'll be around for the rest of the week. Thanks.
Thank you, Matt. Our next speaker is going to talk about asteroid mining. Please welcome Alexandre Meurisse from Origin Space.
Thank you, Abigail. I don't have the clicker. Thanks. So good morning, everyone. My name is Alexandre Meurisse. I'm a space resources engineer at Origin Space. And I'm here on behalf of the CEO, Meng Su, who unfortunately could not join today. But I'm going to give you an overview of the progress of the company on asteroid mining, where we are and what are the next plan of the company. So you may not all be familiar with what the company is doing. So Origin Space is a Chinese company. We are based in Beijing, Shanghai, and Nanjing. Now we open offices in Luxembourg and UAE as well. And this is the first commercial company in China dedicated to use space resources. So really the company has a vision to, in the end, utilize material resources from near-Earth asteroids, mainly water and metals, to bring back and contribute to a broader space economy. So the company was founded by Meng Su, Tianhong Hu, and Xiaojia Zhang, three top scientists who have received a lot of prizes in astrophysics from Harvard and in the US, from NASA, and also later in China. And they are backed up by senior aerospace people from the Chinese space industry who've been working for 20 years. So basically, the company is led by top scientists and people who know how to fly stuff into space. So far, this has been quite fruitful because also the company is quite young. We have 6 satellites in orbit, with the first soft X-ray band detection satellite, and we have a telescope in a UV and ultraviolet band. And we had the first commercial demonstration of debris capture as well. In terms of funding, it's a private company. It's received tens of millions of dollars from pre-seed funding. Next round of funding will come soon. And we are, in terms of collaboration, the company is really open to all sorts of collaboration in the field of aerospace, and we are trying to create partnership worldwide. So that's about the company. So the progress so far, I said we have 6 satellites currently in orbit. So the first 2 on the left were more like partnership with university and other Chinese aerospace company to start to get some experience about some hardware compounds that were then later used in Yangwang-1, which is the first, let's say, full satellite of the company, so Yangwang means to look up. So it's not doing Earth observation, but it's looking the other way, trying to get information from asteroids to populate later, you will see a database. So Yangwang-1 is the first of a constellation, so there are more coming. We are also ramping up by developing a factory chain, being able to drop down the cost and mass produce satellites for such application. So of course, gathering data is one important aspect of asteroid mining, so you know where to go. But at some point, you may want to capture this asteroid to bring it back to an orbit of interest. And that was the first demonstration of NEO-1. As well, we want to be on the market for everything which is about cleaning low Earth orbit, so about debris capture. So NEO-1 was the first private satellite that just drop a debris and capture it with a net. You will see in a second. So that was in 2021. And in 2022, we had the soft X-ray detection satellite, and the EcoCapsule was also a student project where we grew some plants into space. So that's how we start to build up capabilities and for in-space operation and trying to get some data about asteroids little by little. So with the satellites, the achievement so far was the first optical Alt Sky from China, and so that was with Yangwang 1. And with NEO 1, you can see on the video, we release the debris and can capture it successfully, opening the path for asteroid capture, but also, as I said, for debris capture and cleaning up low Earth orbit. Other observations that were made with these telescopes is we could witness the DART mission and the impact on Deimos. We can also observe like sprite lightning and the main purpose of the telescopes also, so tracking comets and near-Earth asteroids. So that's sprite lightning, and yeah. So now on the launchpad we have Yangwang 2 and 3 that are coming up with more advanced capabilities, better optics, and the idea is that we start to grow up this constellation with having more capabilities for better detection of and better prospecting of asteroids. And as for asteroid capture, we have NEO 2 in preparation, and NEO 2 will capture actually Yangwang 1, which will be at the end of life in a couple of years. So the idea is we use our own satellite as proof of debris to demonstrate debris capture. So of course, as the idea is also for the companies to be present in today's market. We have the long-term vision, but we want to use this factory chain to basically drop down the cost of production and offer services to customers for remote sensing and communication and SAR satellites. So really the idea is to have the vision, but to be present in today's market, where it's in LEO. So from all the data we'll collect, we will populate a database that is currently populated with publicly available data. And this asteroid database, we want to license it to you. So if you are interested in asteroid mining and you want just to get to know straight to which asteroid you want, or you want to get information about a particular asteroid, or you want to know where to go, you could use this database to really save time and effort. So this is a tool we are building up, and we will populate it with the data we receive from our constellation, little by little. Of course, LEO is great, but if we want to mine asteroids, we need to go deeper into space, and we want also to move as the market is moving to lunar economy and to the opportunity of International Lunar Research Station or Artemis. We want to be able to be there as well. So we are developing some capabilities for lunar sample and return. So we are developing the M2 rover, and which has about 200 kilograms payload capability, with the ability to do the characterization on site, taking samples, and having its own capsule for sample return at its back, which will with a liquid oxygen and methane engine. So that's for, let's say, the intermediate step and going to the moon. As of course, we want to also to get some more data by prospecting samples from asteroids. We are looking into how we can extract water at different scales from the small sample to larger scales and for commercial application. So here we are ramping up also these capabilities, and I hope to be able to present you a bit more next year on this topic. So that gives you an overview of the company's vision. And before I close my talk, there is, I think, a video now which gives you, which sums up what I presented and gives you the modest vision of the company. Thank you. So if I could have the video. Okay, well, I think it's I can present the video later.
Sorry about that video, but well, I just remember you that if you have any questions, even although we don't have a Q&A part of this in this session because it's really packed, just make a note about that, and if you see the speaker, just go to talk to him or her, and also if you or if the speaker is online, you can just simply send it online, and he will or she will reply to it. So we have the next 3 talks are shorter talks, and 2 of them are going to be online. So I want to see if Ben Jackson is online.
I am.
Okay, yeah, I think we can hear. Yes, we can hear you and we can see you. So Ben Jackson is going to talk about water ice prospection missions on Mars. Thank you. Welcome, Ben.
Well, hello, everyone. As you said, my name is Ben Jackson. I'm a geologist and recent master's degree graduate from Colorado School of Mines. And on behalf of my research team that I was part of at the school, it is truly an honor and a privilege to present to you all today. Next slide, please. So what we're talking today about is the Mars water ice prospecting mission. And the centralized objective of it is to achieve a water ice inferred resource classification to justify future economic development. And to do that, what we're going to need to do is to, as a society and as a world, just kind of come together and, agree to develop a space resource classification system similar to kind of terrestrial-based systems. The one I mentioned here is the JORC code, which is an Australian kind of resource classification system. Now, why is this mission important? Well, the central thing is that water is a keystone resource necessary to establish a human presence on Mars. It's essential for everything from human consumption to propellant and oxygen generation, agriculture, and even radiation shielding. And where we chose to do this project and to focus on was the Flagramontes region of the northern mid-latitudes of Mars. It was chosen because it has identifiable glacial morphologies, large size of targets and relative ease of access. It has an abundance of satellite data from things such as the Mars Reconnaissance Rover, among all of the other kind of orbiters that are now currently going on around that planet. And detailed analysis, and we conducted a detailed analysis of the individual feature, which is a lobate debris apron, which is a remnant glacial feature, to identify the safest potential landing site. If you look into the upper right-hand corner, you'll see the proposed landing ellipse, which is based on an ellipse the same size as what was used for the Perseverance rover landing. As far as mission architecture goes, what our team envisioned was a dual rover system with phased landings and splitting up duties into 2 separate rovers. The initial scout rover, which would identify potential drilling sites, and then followed up by the Prosperity rover, which is a drill rover that would actually drill in through the surface of the lobate debris apron, through the overburden, and then down into the ice layers beneath. And then identify the composition and quality of the volatiles that are held within. The instruments shall analyze the samples, identify the composition, and then also it'll be able to give us our first real taste of being able to define depositional history of a glacial feature on Mars. Next slide, please. Thank you. So the concept of operations for the mission, as I mentioned, is split up into two phases. The first being the landing phase. So when Clairet lands within the landing ellipse, once it's gone through its testing and whatnot, what it'll do is it'll do intermediate starts and stops, taking neutron spectroscopy measurements when it stopped, and take ground penetrating radar and then also visual and near infrared readings as it's moving along from location to location, making stops approximately every 20 meters from the previous measurement. When it's identified a specifically interesting potential target, it will deploy the explosive excavator, which would be effectively it sets a depth, it sets a charge, moves to a safe distance. The charge explodes, creating a small crater, which then the device would go back to and examine the fresh crater to kind of identify features of the overburden and potentially, hopefully, although doubtful, actually getting down into the ice beneath the surface. As it does that, it will. The minimum goal is to make it 1 kilometer across the surface, and then hopefully to get far beyond, and continue collecting data for as long as the device actually lasts. Through that process, it will identify one or multiple potential landing sites. One of those sites will be defined, and that's when the Prosperity rover will descend to the surface. Once it's landed and gone through its systems checks, it will move to the actual location and deploy the Honeybee Robotics based Rebel drill system, and with the goal of reaching a minimum depth of 25 meters, which is based on current understanding thought to be the approximate distance of ice across many of these features, and it will stop every 10 centimeters to pneumatically remove cuttings and do detailed analysis on that material to define many of the key parameters that will kind of control the process of the drilling and also the chemical makeup and some of the actual compositional limits of the materials. And then hopefully, if things work out and in the final version of our notional project, the Rebel device would have the ability to reverse, respool, and then drill additional targets that have been defined by the Clairet rover. Let's see, I believe if you would move to the next one. Thank you. So this is pretty much just a very brief overview of the system specs that were designed for each rover, along with just a general prospect summary. So the key thing is that to reduce general costs and development times, most of the non-essential or non-instrumented portions of the rovers will be based on pre-existing heritage technologies, such as the landing systems, the mobility systems from the Spirit and Opportunity rovers, or Perseverance, depending on what device we're looking at. In the case of Clairet, it is generally platformed to be similar to the Spirit and Opportunity rovers with similar power and mass ratios. And actually, it's somewhat lighter than Spirit and Opportunity would be. It is solar-based with an isotopic heater, with the plans of operating up to 4 hours in an average Martian day. We believe that, at least we estimate that the initial 1 kilometer phase that we would attempt to reach with our scouting rover would take about 2 to 3 months, and then would continue for as long as the device would last. And considering how long Spirit and Opportunity did, that could be many, many years. As far as Prosperity goes, the Prosperity rover was platformed similar to the Perseverance rover. There's one major difference to it, which is to run the different components, such as the spool motor, the drill assembly, and the pneumatic cutting systems. It takes a lot more power than, say, a Perseverance rover. So where Perseverance used approximately an average of 110 watts, we have seen that it could take up as much as 2.8 kilowatts, which would remove the possibility for anything such as solar power. With that in mind, we decided to employ a kilopower style reactor, highly enriched uranium nuclear reactor. It would generate up to potential 4 kilowatts of electric energy. It is quite mass intensive and would take up a majority of the device's space, but it is actually close to within the range of it's only about 75 kilograms heavier than, or more massive than, Perseverance in current estimates. So to keep this somewhat short, to summarize, the main objective is to achieve a water ice inferred resource classification. To do this, we need to actually form a consensus to develop a consistent space resource classification system, something similar to the JORC code, the Australian JORC code, I should say. Using existing technologies can reduce development time as well as costs. The dual rover architecture allows for some limited redundancy based on using complementary instruments, and would allow for unmatched data quality and fidelity of data for resource identification. This would also be a great flight test for a mobile kilowatt uranium thermonuclear reactor, and would be a blueprint for future resource development missions. Thank you guys for your time. I appreciate it, and I look forward to hearing questions from you all.
Thank you, Ben, for your nice talk. I just want to remind all the speakers that please, it's very important that we keep the time. So yeah, be aware about that. Thank you. Our next speaker is Lanre Logan, that he's from ESA, and he's going to talk about the ESA elements of the Mars Sample Return Campaign. Welcome, Lanre.
This way. Perfect. Okay, good morning, everybody. Thank you very much for having me. My name is Lanre Logan, and I'm a trainee working at the European Space Agency on the Earth Return Orbiter, which is one of ESA's elements of the Mars Sample Return Campaign. And I'm going to talk to you about an overview of this campaign and how the resources it brings will be able to help us within the industry. The clicker, there we go. So, the Mars Sample Return Campaign is one of the most complex missions out there, essentially a cosmic relay race made up of 3 separate flight elements, and made only possible through this international cooperation between ESA and NASA. So the first element of this campaign was the M2020 package, which included the Perseverance rover. Now, this rover is currently up there, driving around on the red planet, and has already collected 19 of these samples, 10 of which it's already deposited on the Martian surface in a backup depot just finished this past January. Now, the next element of this mission is the Sample Retrieval Lander, or SRL. So once SRL has landed, the Perseverance rover will hand-deliver its cache of samples to the lander, and then ESA's Sample Transfer Arm, or STA, will grab the samples from the surface and load them up into NASA's Mars Ascent Vehicle, which is the rocket that will be launching the samples up from the surface. Now, if Perseverance isn't still operational by the time that SRL lands in about a half-decade or so, then the backup mission is NASA's Sample Return Helicopter, which will fly over to the backup depot and then deposit the samples again in front of the Sample Transfer Arm. Now, if all of this wasn't complex enough, the third and final flight element is the Earth Return Orbiter, or ERO. So once the Mars Ascent Vehicle has launched the samples off of the surface, ERO will be there viewing the launch, and it will listen out for what we call the beacon, which is essentially some radio frequency beeps, which the Mars Ascent Vehicle will emit, and ERO will listen out for these and use the frequency and cadence of these signals to recreate the orbit that the samples would be in. And analyzing this portion of the mission is what I'm working on in my traineeship, actually. So once ERO has figured out which orbit the samples are in, it will home in on this orbit, and using its cameras and LiDAR, will rendezvous with and capture the samples with NASA's capture and containment and return system, which is on top of the satellite. Then begins ERO's long journey home using its electric propulsion engines. So in about 2033, the samples are currently planned to land in the Utah desert, and they will be taken to the as-yet unconstructed sample handling facility. The first thing that will happen once they've been taken into this is called the Sample Safety Assessment. A lovely bit of alliteration there. And in this assessment, the samples will be sterilized and X-rayed to get a better understanding of the internal structure within them. Then it's time to open up the samples. So as you can see, within each tube, there is about 2 to 3 centimeters of empty space, which will, of course, contain some Martian atmosphere. So again, some extra data which we can use to classify them. The samples will be taken out of the tubes, weighed, and photographed. And all of this information will be put into a catalog where scientists will be able to pass through the information of these samples and use it to decide which they may want to propose which they may want to propose to take to study further. As I'm sure you're all aware, these will be the first pristine samples taken from the red planet, and will be able to give us an unprecedented insight into the geological history of the planet. And some of this knowledge, we only have maybe error bars of 500 million years or so of the formation and evolution of Mars. So these will be very key resources to understand this further. Still, not just the past of the red planet, but also the future. These samples will give us a great insight as to how humans will be able to use them during future exploration. We might gain insights into how its mineral-rich nature may be able to be used for processing and in situ resource utilization. Or we could even end up finding out about sorry. Yes, or we could even end up finding out about the shape of the dust and whether it could cause a problem in the seals of our future habitats or spacesuits. Overall, the Mars Sample Return Campaign is a complex and ambitious mission made possible only through the use of this international collaboration. It will help us to unlock some of the Red Planet's most closely guarded secrets, and it will give us an unprecedented helping hand into understanding how humans may use the resources there in the future. And in about a decade, when we return the samples back down to Earth, who knows, maybe some of you out there will be some of the scientists ready to analyze them. Thank you.
Thank you, Lanre. Beautiful presentation. We continue on Mars. Our next speaker is Clairet Guerra, that she's joining online. Are you there, Clairet?
I am here. Can you see me?
Yeah, we hear you and we see you really nice. Well, the talk is about Martian hydrated minerals from the current state to a proven reserve, a scientific mission concept. Welcome, Clairet.
Thank you very much. On behalf of my teammates and myself, thank you all for joining and dialing in. Next slide, please. As Abigail mentioned, we're focusing on advancing the knowledge from a known resource to a proven reserve. This is framed in a scientific mission concept trying to address all the necessary variables and parameters to push the knowledge forward, but not to fulfill the entire mission in one single go. How are we planning to do this? And what have we done so far? At the end, I will also show you where are we targeting our current efforts. First of all, we part on relying from the current knowledge on the detections that exist on the Martian landscape. From this, we rely on algorithms and scripting to proceed to cluster the regions where we have the higher detection counts to select these places that could be potential candidates. As you see, we have 4 there, we have more selected. But on top of that, understanding where they are, what it's in those locations, we also need to address how accessible are these locations. Can we really get there? And can we really proceed with further exploration and later on excavation and collection of the materials? And for this, we need to add additional set of parameters like, for example, roughness of the terrain, slope of the terrain, rock abundance or different rock metrics, and solar incidence as to some reliability on energy sources for our missions. Once we have combined what's in there and whether we can access, we can define our final target. Needless to say, this is the place that we choose for our example and for our current work is just to make the example of the mission implementation. But this type of work can be deployed and replicated in any other location that follows the same restrictions. Next slide, please. Once we have selected the site, we are going to land a rover in that area. It's a wide area with low resolution reliability, and we need to increase that fidelity. How are we going to do this? From that rover, we're going to use an a mounted on unmanned aerial vehicle. And this is going to try to replicate that remote sensing detection, but in a higher resolution in a region close to the perimeter of that rover. With this information, we're going to constrain the polygons or delineate an area that will later on help us constrain the regions where we can delineate the polygons that will serve for a borehole array for a future drilling campaign. Next slide, please. Now, this is a very high-level concept of operations. Please focus right now on the data acquisition line, which is the red line in the middle. And the faces in the different blocks were left intentionally so that you can see that this is not a one-man mission. This is a multidisciplinary effort. We already went through the UAV presence, we know that there is a rover. There will be drills participating in the mission, and there will also be additional sampling in situ. Because apart from getting knowledge of the spatial distribution of the hydrated minerals and also depth information to be able to construct a volumetric concept, we need to address the purity of the resources that we're analyzing. And for that, we require some in situ testing that tells us how much water content can be extracted from the materials that we're analyzing, from the geological deposit we're analyzing. All of this data acquisition information is framed in a proper communication setup that allows us to transfer the information and do in situ data collection in initial processing, and later on transfer information to Earth and do some additional post-processing. Next slide, please. Our current efforts are targeting providing adequate parameters, adequate requirements, and adequate metrics to make sure that we can take advantage of what technology it's already available off the counter, like off the shelf, and what kind of technology needs to be adjusted in minor or major ways. For example, customize drills from the oil and gas industry and make it fully targeting hydrated minerals. On top of that, we have a prioritized list of tests on Earth using analogs and an outline of what kind of initial testing we should deploy on Mars if this shall take place. Final slide, please. Next slide, please. The final comment is that no single mission will not be enough, but this work can definitely push the knowledge forward in this field and lay the ground for further and more complex work. Thank you very much for listening, and I'm happy to take questions offline.
Thank you very much, Clairet. The next speaker is Jim Hondros from Deimos Space Resources. Is Jim here? Okay, yeah. He's going to talk about shifting the paradigm of Earth resource development. Welcome.
Good morning, and thank you for the introduction, and thank you to the organisers of this fantastic conference and for the opportunity to present today. I must admit that I feel a little bit overawed and slightly nervous to be here presenting at a space conference. And the reason for that is that I'm not a space guy. I'm a resource industry guy and have been my whole career. I've got almost 40 years' experience in operational, corporate, project and advisory roles, ranging from exploration projects in Jordan, Mongolia, Mauritania and outback Australia, through to billion-dollar new start mining and processing projects, through to expansion and optimisation projects in multi-billion-dollar projects. I've also worked for many years in the nuclear industry. My colleague Mark Saunter has a similar background, but he also has space industry experience as co-founder of Deep Space Industries. Mark is also a recognised guru in asteroid mining and resources. My other colleague, Kirby Eichen, is the space guy. He has a career in space business development, being a leader in space insurance, through to being the current chair of the National Space Society, taking over from Buzz. He was also a co-founder of Deep Space Industries. So on behalf of Mark, Kirby and myself, and our other current partners, I would again like to say thank you to the organisers. In this talk, I'd like to provide you with an update on our space resource development project. In particular, the first phase being our proposed prospector mission. As you can see from our company name, we're not very subtle in identifying our target. This is the topics I'd like to cover. I'm not going to read my slides. You can read them at your leisure. I really just want to pick out some of the key points and share them with you now. So our company, let me start by saying that we're an Australian company that aims to think about space resources as just resources. We think that the approaches used on Earth, honed over many generations, are entirely applicable as the starting point for space resource development. Our first capital raise is imminent, and we are very excited about this. As a commercial entity, we are about practicality, we are about simplicity, and we're about sustainability through profitability. In line with the theme of this conference, we know that we cannot succeed alone. And to continue, we need collaboration and partners. I'd just like to share some of our highlights to date. We don't have a lot of money, but we have had some wins. We are very pleased to say that our company and our project have been recognised by the Australian Space Agency, and we are looking at further collaboration and hopefully some announcements in the near future. One of our other achievements was to hold a symposium that we ran last year on resource missions to solar system small bodies, hosted at the University of Adelaide. We had invited attendees from the US, from Japan, including some JAXA professionals who are involved with the Hayabusa missions. Importantly, we had a number of mining industry practitioners in attendance. In particular, we had a manager, an exploration geology manager. We're hoping to run that conference again later this year. The third key point I'd like to make about our company is that we continue to learn and to iterate our project. We're not fixed, we aim to continue to develop and improve our mission scopes. Overall, we want to reduce complexity. We want simplicity, and we want to use existing hardware and technology. Our innovation. We think that our innovation just lies in the way we think about space resources. This might sound really, really simple, but seeing situations and challenges through different lenses enables us all to see situations with new insights and differently. We also recognise the past, and we're prepared to stand on the shoulders of giants. And the photo shows us in conversation with Professor John Lewis, the grandfather of space resource development. The market. We all know the market exists. And our aim of our project is to be part of that market, is to be part of the supply of raw resources to the expanding space economy. Yesterday I heard a presentation where the comment was made that resources are enablers. We think that sustainable resource supply is more than an enabler. It is the platform upon which the space economy succeeds or fails. And guess what? Our target is Deimos. Over many years, we looked at asteroids as a source of resources, and they still are. There's a huge amount of resources available in the asteroids. However, Deimos, when you do the maths and you do the sums, is a more enticing target. It is highly prospective, and in terms of energy requirements, on certain occasions, it's actually easier to get to and from than the Moon. Our roadmap. Our project roadmap is entirely consistent with a roadmap that you might see for a terrestrial resource project. First, you go and have a look. You prospect. You kick the dirt. Then you conduct a desktop pre-feasibility study based on your first look. That should give you sufficient impetus for a first stage investment where you do a demonstration mission to collect sufficient information to inform a final feasibility study. The final feasibility study, in fact, acts as the justification for final project investment. It's interesting when we did the maths and the sums and the costs on the back of an envelope, but the cost of a project like this is very similar to what you would do for a large-scale project on Earth. So the funding mechanisms are actually in place. What I'd like to do is, while we have a full-scale resource project in mind, the first step is to go and have a look, is to do the prospecting mission. What we want to do is to go and feel the dirt. Our plan is for a simple orbiter and a lander package containing a suite of instruments that would provide information for resource clarification and resource development. Note that this is slightly different from a science package. In our case, the data from the instruments aims to inform the investment decision. We've scoped the resource prospectivity instrument package and think that is likely to be useful for any prospective prospector mission. We see a lot of benefits from conducting a commercial project, and firstly, a simple prospector mission. But we all know that. We all know the benefits of any of these projects taking off. However, the one big advantage we see, or the one big benefit we see, is bringing people and components and systems and parts into a common objective, a common achievable objective. And as I said earlier, we know that we can't do all of this and we continue to look for partners, but focusing all the energies on a single mission is more than likely going to produce success. So let me summarise. Our preliminary investment for the Prospector mission is imminent, and gee, we are excited, even though it might not look like it. We have a target launch date late 2026, but we are being challenged by some of our partners and investors to go for it and go for late 2024. And to tell the truth, there's nothing quite like a challenge and pushing. But again, I'll say it again, we know that we can't do it alone, so we continue to look for partners and collaborations. But most importantly, we know we can do this. This is a resource project. It just happens to have a long supply chain. So with that, I'd like to say thank you for the opportunity to present today.
Thank you, Jim. Our next speaker is from ESA, and he's going to talk about the ISRU demonstration mission, and it's David Beans. Please, welcome.
Hi, good morning. Thanks very much for attending the talk. Start with the fact that it's always a privilege for all of us who work on the ISRU demonstration mission to present what we have been doing. I mean the present and also the past persons. There's a little bit of something of everyone who has worked on it still present in the mission. So I discuss, our previous contractors, our current contractors, so on, and members of the ESA team. So thank them also very much. So I'll start with a bit of a story so far. I mean, we've had parts of our journey where that have moved very fast, parts of the journey have been quite windy, and I mean, I recalled the original trade trees that we had in the very first feasibility studies to understand what we didn't know, and what we wanted to find out was, a bit more like a willow tree, so it had many branches. So we have gone through all this process in the very beginning to understand basically our knowledges and also have a methodology for comparing processes. This led us to 3 particular processes where we conducted a phase A studies on the feasibility of these processes to understand their implications and the specific functionality requirements. In parallel to this, although was not personally involved in these things, we have internal ESA ground demonstrators and also industrial contractors for the hardware know-how and demonstrators during this period. And this has all fit quite nicely together in a nice synergy with everyone working in these parts as well. To feed also into our demonstrator study, we also conducted a number of pilot plant-like studies to understand the user cases and feed these back into our demonstrators so our demonstration makes sense. Leading to the current status where we are currently in a phase B1 working towards our system requirements review with our winner of our challenge that we held in 2019-2020 to choose a Thales UK as our prime contractor. From the standpoint of being requirements driven with no specific ESA process recommendation. So I won't really deal with the process that we use. I'll leave that to the expertise of my colleagues in these processes. So just to summarize, in the top left and the top right, these are our first drawings of our payload, our first sighting cases. We start to look at a little bit more of the hardware, so the piping, the tanks, the hardware, the valves and seals and so on. In the bottom left is our first CAD drawing of a pilot plant mission case sitting on top of the Argonaut, so you can get a sense of scale to the left. And also in the bottom half, this is some pictures from literature, which takes the regular symbol and presses it into a more solid block. So we looked at this. So this is basically where we've got story so far. So in terms of the demonstration mission itself, we want to obviously land and commission our payloads, which is top left and top right. In the bottom left-hand corner, we would acquire some regolith. And in the middle of the picture, we have our loading via reactor, and then the magic happens in the bottom right with the oxygen production and the metal production and so on. And more ultimately, with bearing in mind a proof of capability is the overriding goal of the mission, and also with broken down into understanding the material from which it is from, and also the extraction of a usable resource and proving its technical feasibility, and naturally trying to generate a level of awareness and scale and realism of the whole thing for the future. To break it down a little bit further in more detail in terms of requirements, our current objective is to do 5 samples. The level of detail and what these 5 experiments will be in these 5 samples requires a little bit more effort from both on our side and in the scientific community, and also the engineering community to understand what we really want to gain from these experiments and how to couple them together. Because obviously some experiments will have synergies with others and some experiments will want to be separate. So this obviously is the next stage as we go further into phase B to understand the level of detail and what we should do with these experiments. So 3 to 5 is our current objective. For this, we want to look really at the analysis of the product gases, and also what's currently under study is the composition of the solid materials before and after the reduction process. So this is an area which we are looking at and see what we can do with the current design with respect to measuring the output from a solid perspective and inputs to compare. And we want to repeat these under similar conditions to demonstrate a level of repeatability. Because obviously a loading and unloading of everything is a very much part of a use case in the future. And this is also very much a big part of the demonstration, is gathering the sample in its relevant environment, producing it and seeing if we can achieve an optimal process in this case. And all to do in 10 days or so, Earth days. I keep making a mistake of saying 10 lunar days, but it's in fact 10 Earth days. So to look at the payload itself, I do apologize for my own crude drawing. It does by no means represent the level of detail and effort that has gone into the actual configuration of the payload by our industrial partners. So I do apologize for this. So basically, you can see it is 800 by 300 by 300 block, which is not insignificant in size, and we do make an effort to reduce this size. So we begin with an regolith inlet where we load regolith. I mean, I keep it in very simple terms, and we can discuss detail away from the presentation if you like. And then the step of removal of volatiles. We handle the 5 samples and load them into a reactor and make the reduction process. So we have a transfer and processing system, a reaction plant, fluid gas and management. So in the current baseline, the instruments are based roughly on the Barthélemy and the Prospect-based gas analyst packages. But we want to look also into including obviously instruments to measure the solids. And this is something that we are discussing with our current consortia of how best to do this. I mentioned the power control. It's not an insignificant unit because of the power involved and the distribution involved. So it's very much dominated by power distribution here. Right, I'm going to do something which takes me a little bit out of my comfort zone since I miss a couple of slides. So I'm going to take advantage of the big model on the left-hand side. So if online you don't see me anymore, I do apologize. But I just want to just point out now for the purpose of the mission. So I'm taking a personal risk. I hope this goes okay. So we looked at 3 mission cases for the mission, how to accommodate the payload. So I want to focus the audience attention on the mid plate itself. So in the Argonaut case, we can consider a mounting on the top deck, or we can consider a mounting on a side panel, or we can consider a mounting with a cutout where we slot the reactor into the deck. So in the first case, on the top, we add a system-level thermal mechanical adaptation, which adds about 18 or so kilograms to the mass of the payload. If we then mount this payload still on the side face, this will add about 32 kilograms of mass to the payload. If we make the cutout, the thermomechanical overhead is somewhat more like 15 kilograms. Beyond this, we have a robotic acquisition system which needs to gather a sample. So in the 2.8 meter high Argonaut case, this is an additional mass of around 19 kilograms which we need to provide in the payload beyond the basic building blocks. And if we have a smaller lander, It's around 12 or so kilograms, so 1.8, 1.5 meter deck height, or maybe a mounting position on the side. So all in all, for the case of the top deck, it is around a 90 kilo payload. In the case of the shear panel on the side, it's about 110 kilograms or so payload. And on the cutout, which perhaps is the optimal solution, it's around 80 kilos or so. So I wanted to draw attention more in this presentation to these mission aspects, and to dwell maybe on the detail of the design of the payload in a more offline sense. So basically, to conclude the outlook, we work towards in the summer our system requirements review, and then we then hope to kick off critical technology breadboards, and the mechanism also in the autumn time. The mechanism for this from the ESA side is an engineering change request to our prime contractor, where our prime contractor will issue a number of invitations to tender for the critical technologies. Hopefully, within the next couple of years, we'll reach a level of technical maturity to enable our member states at ESA to take a decision at appropriate time of a flight model and a mission. Of course, this is at their discretion, and the timing of this is entirely up to them. So, just to conclude, it's a notional schedule. I hope the dates are all in line. So, just to conclude, so we have a preliminary definition. There's a current stage we are at with the 60 to 80 kilograms to 100 kilograms. It varies depending on mission, but the building blocks are fairly more stable in mass. We'll begin the critical breadboards very soon, we hope, and we've identified these 3 mission options. So we don't really talk about really specific landers anymore. We talk about really accommodation locations, so on a top deck, on a shear panel, in a cutout. Aiming for this 50, 100 grams to characterize the gases. And one thing we want to say that we're very much understudy, really, and it's a little bit less defined than the reduction process itself, and the reactor is the measurement of the solid in and out of the production process. So this is what we understudy. So if there are any questions, of course, please approach me outside and offline, of course. So that was the end of the talk. So thanks very much for listening. I think we're all happy that you have the interest to listen to us and our demonstration mission. Thank you.
Thank you, David. Well, exciting times are coming. So our next talk, that I must say that is not the last talk. We have another talk after this that is not put in there. It's a little surprise. But our next talk is also from ESA. It's about the pilot plant Concurrent Design Facility, and it's going to be given by Giorgio Magistrati. Welcome.
Okay. Hi, good morning to everyone. I am Giorgio Magistrati. I'm replacing George Alves, that was supposed to come here, but indeed he couldn't because he's attending another conference. And the intention is to present to you the main outcomes of internal study, ESA internal study that we have performed in 2022 on the ISRU pilot plant. ISRU pilot plant is not indeed an ESA idea. ISRU pilot plant is one of the main elements of a global exploration roadmap that is defined by the International Space Exploration Coordination Group, and together with operational ISRU plant. The ISRU plant, the full-scale ISRU plant, is supposed to produce up to 50 tons of propellant per year, while the ISRU pilot plant is thought to be a scaled-down version of the operational plant, but still basically quite a significant beast, because they should be able to produce something that is between 110 and 100 of that amount. So we are talking about 450 kilos up to 4.5 tons of propellant or oxygen per year, and as well basically to guarantee to be operational for at least 2 years. The important point with respect to what has been presented before by my colleague David is that ISRU-DM is essential to demonstrate a capability. In this case, what we want to have, to implement with the ISRU pilot plant, is to create a subsystem that is an integral part of a lunar exploration scenario. So in some way, this ISRU pilot plant has to enhance and expand the mission scenario itself. So for example, extending the mission duration. It's also important to say that clearly there is something that is aligned with what has been presented before. So the ISRU pilot plant that we have studied is based on the same process that is indeed used by ISRU Demonstrator, that is the FFC Cambridge process based on molten salt. Okay, as I was saying before, the primary function of the ISRU pilot plant is to produce oxygen, but we have as well basically some additional or optional functionalities or requirement to produce oxygen for a life support system, and as well to produce metal and metal alloys that can be used for other important tasks, like for example additive manufacturing, solid fuel propulsion, energy storage and generation. We have performed this study clearly considering some assumptions. One of the most important one is that we want to have it delivered to the moon surface by Argonaut. In some way, basically, we have to shape, to define the design in order to be accommodated on top of the Argonaut lander. As I was saying before, the capability is between 1.5 and 1.8 ton. And as well, basically, we have assumed that already on the lunar surface, other two important elements that are necessary in order to operate the ISRU pilot plant are present: the charging stations or the power stations, and as well an excavating rover that has the main task to feed the ISRU pilot plant. As is indicated here, we are running parallel studies, pre-feasibility studies on both the two services that are necessary. Clearly, we do not exclude the fact that this type of services, power and regulate provision, can be indeed basically provided by other elements, other assets that could be made available by other agencies. Clearly, we want to operate in international scenario. Another important assumption is the fact that we are assuming that astronauts are indeed present in order basically, for example, to set up the pilot plant and as well basically to be involved as well in to collect and to use the products stored at the pilot plant. The launch date is not indeed supposed to occur before middle of the next decade. And it's also important information that in 2022, last year, we went through a list of mission studies to become phase B1 in the future periods of the exploration program of ESA, and the ISRU pilot plant is one of the 9 mission elements that are candidates to become phase B1. As I was saying before when I was presenting Argonaut mission, is not indeed a candidate for mission number 1, but is supposed to happen end of this decade, probably neither for mission number 2, but is a really credible candidate for mission number 3 and 4. What you have here on the right is as well a work breakdown structure of the ISRU pilot plant. It's nothing, I would say, really new in the sense that indeed, as for all the space missions, we have different segments, the lunar surface segment, the ground segment, and the launch segment. Obviously, what probably I forgot to mention before, we are talking about delivery, not a deployment. So the idea is that the ISRU pilot plant will remain on top of a lander. Concerning the mechanical concept for the manipulation of regolith in ISRU pilot plant, we have trade-off different options, and one of the options is we are presented. That is the one that is considered a baseline because he tried to reduce to the minimum the number of joint mechanisms that are necessary, and is composed essentially by a crane and a carousel. As normally done in the CDF study, we are not only basically defining the requirement, describing the payload in terms of functionalities, but we have as well basically defined a first version of the concept of operations, and as well we have defined the budgets, essentially in terms of mass, power, and volume envelope for all the different elements that are composing the payload. We have clearly more detail. We are indeed now finalizing the CDF report that can be also basically distributed to ESA member state or to industries entities that are located in an ESA member state or participating state. That's all from my side. I am here in the case that you have any question.
Thank you very much. It's really nice to see what ESA is doing for going to the moon back. Well, during all the event, we've been already hearing some big news that is happening next week. So this is very important to me, I must say. So I would like to all of you to give a nice welcome to Julian Lamamy from ispace, that he's going to talk about the oncoming Mission 1. Welcome.
Good morning. Can we go on the main slide, please? Okay. Yeah, so I'll give a recap on M1. You see a picture here of the lander that is currently orbiting the moon. So I'll tell you the story of how we got there. Next slide, please. Actually, I'm in control, so yep. Here we go. Before we talk about M1, this is a picture taken last year of our team in Luxembourg. So we're by the train station, 10-minute walk. This is ispace Europe. We develop lunar rovers, data analytics, space resource technologies, and also a lot of business development. And you see about 20 people here. We're 30 people today. But this is about the size of the entire ispace team when ispace decided to invest a significant amount of resources to develop a lunar lander. That was about in 2017. So that's when I joined as well. Because of the difficulty of sending their own rover, Storato, to the moon, they couldn't find a reliable transportation system. ispace said, okay, we'll raise $100 million in Series A, and we're going to do our own transportation system. This was the vision in 2017, and 5 years later, in December 2022, this is our M1 spacecraft mounted on top of the Falcon 9 rocket that took us to the moon in December 22. And I really want to highlight, this is only about 5 years. And 5 years in the space industry is very short. And it's even shorter when you have to grow your team from 20 people to over 200 people. You have to design the spacecraft from scratch, develop all your processes, find your suppliers, find your assembly facilities, develop all your procedures, do your qualification models, test them, and then do your final flight assembly, which was actually on time, which is, even for any spacecraft project, an amazing achievement. And on top of that, we had some fun surprises, COVID, major supply chain disruptions. So to me, the greatest achievement so far of ispace is being able to develop this spacecraft from scratch in just about 5-6 years. And on top of that, now it's in lunar orbit with the prospect of possibly achieving a landing next week. How we did this, I'll share a couple points there. First is our vision: expand our planet, expand our future. Everybody at ispace is really committed to this. We see ourselves as contributing to the future, where the moon is not only for further science exploration, but for human presence, human activity, space resources, of course, supporting new business models, new entrepreneurship, a new economy. And supporting this vision, we have what we call our ways. We have 3 ways. The first way is what we call involve others. So yes, we designed, developed, tested, assembled this lunar spacecraft ourselves, but we relied a lot on, poor video editing, but a lot of key strategic suppliers. We have Draper Labs for the guidance navigation control software. We have ESA supplying the S-Tract ground segment. And we have Ion Group, which you just saw there, supplying the propulsion subsystem and also the AIT facility. So our team spent about a year during COVID at Lempelshausen, Germany, assembling the flight model of our spacecraft, and then to Munich at IABG, testing this flight model. So the spacecraft that's currently orbiting the moon is the first and only lunar lander ever assembled and tested in Europe. So it's a Japanese design, but tested in Europe, launched from the US. And going to our second ways, beyond convention, it's a lander that's carrying customers. That is truly the distinguishing feature of this mission. It's the first mission to carry paying customers to the moon. Chief among them, the Rashid rover payload from the Mohammed bin Rashid Space Center. JAXA also has a rover. But again, the really cool thing here is that it's not only space agencies. We also have private companies. NITER, a Japanese company. 3 Canadian companies, Mission Control Space Services, Canadensis, NGC Aerospace. And closer to this crowd, if all goes well, ispace will be doing the first commercial transaction of a space resource. We have a contract between iSpacing and NASA for supplying NASA with commercial regolith, with regolith, and iSpace Europe also has their own. So a lot of pioneering, groundbreaking things happening with this mission. It's not just about the technology; it's also about the business and establishing new transactions for space resources. This all led to the launch. So it's our Falcon 9 rocket. We're sitting on top December 11, I believe, 2022. And then this is when we left the nest. So you can see us on the left, they're attached to the rocket. On the right is the video feed from the Falcon 9 as we're separating from the launch vehicle, and we have to fly with our own wings. And then on our way out towards the moon, this is a picture taken by not our camera, even better, it's taken by one of our customers' camera, Canadensis. Their camera is our payload, and they took this really cool picture of the Earth as we're leaving. And I may be mistaken, but I think that might be lunar flashlight on the right there. And then as we had a cruise of about 4 or 5 months, we defined some steps along the way to get people excited. So from launch all the way to various maneuvers. And today we're at success number 8 right there. We're in a circular orbit around the moon, 100 kilometers altitude. And next Tuesday will be our first attempt for the real one, the real success number 9, completion of the lunar landing. So we're really, really excited to just be in this position of attempting this lunar landing. As I said, it took us a little while to get there. So we separated from the Falcon 9 rocket, deployed our legs, and then took this really roundabout way to get to the moon. We went to about 1.4 million kilometers away. And that's for some fancy orbital mechanics maneuvers that allowed us to use a very low energy orbit in order to get to the moon. So a lot more energy efficient than if we had taken the direct transfer of about 10 days, and which allows us to take more payload to the moon. And I think 3 or 4 weeks ago, we did the real key maneuver, which was the lunar orbit insertion. So you can see the spacecraft getting close to the moon, getting into the sphere of influence of the moon, and then doing a lot of braking so that we can stay in that sphere of influence of the moon. We were then in some kind of elliptical orbit. And then just last week when I was in Tokyo, we did a circularization burn, a 10-minute burn, went perfectly, so now we're on a 100-kilometer circular orbit around the moon. And the last ways that we have, the 3 ways, the last one is proof by action. This is the one that everybody is really living day in, day out at iSpace, proof by action. And we're all very proud of our ops team in Tokyo who managed to recover from a few surprises along the way and get us all the way to lunar orbit. We're also very proud of our team in Luxembourg. Philippe, Sophia, Dan, all of them are here in the crowd, so you can say hello and give them a tap on the back for doing backup operations from Luxembourg. So we have our own mission control room in Luxembourg, our own connection to S-Track, and next week everybody will be rooting for those guys. So next week, this is what we'll attempt to do. It's easy to show on the graph. It's easier to perform. And there'll be a broadcast online, so please tune in. For people in Europe, it's pretty convenient. It's just after work. It's happy hour, so grab a beer and enjoy the show. That's what we'll do. So, yeah. And then the best part is, well, this is the best part, actually, yes. So the best part will be to get this kind of picture from the lunar surface. You know, this is already really cool. I mean, we've all seen the moon. LRO does much better pictures, yes, but this is from ISpace. It's a commercial spacecraft. This one is for the books. And then, yeah, hopefully we'll get one from the lunar surface next week. And no matter what, we get to do it again. And that's what I'm really excited about. You know, we have an M2 planned to launch next year. And then an M3 the year after that, going to the far side. And the M2, the really cool thing is that this one will have a rover made in Luxembourg. So our team right now is preparing for the core model of that rover. Next year, we'll have the flight model ready. So I look forward to Space Resources Week next year because it's about the time when we should be done. So you can tell me whether or not we match that schedule. And that rover will go on the M2 lander, which is exactly the same, more or less, as the one that's in orbit right now. And that rover will perform also a regolith collection, and then we'll do a commercial transaction of that regolith to NASA, because iSpace Europe, we have our own contract with NASA for this, and Carlos Espejel will talk more about that tomorrow. So thank you for your attention, and please tune in on Tuesday.
Thank you so much, Julian. It's lovely to see the development as well, year on year, and to get to know the people. And looking forward to Carlos's talk again tomorrow. I know he's probably in the room somewhere. He usually is, and was name-checked yesterday on a few papers as well. So wonderful. Some of those talks gave me goosebumps. And with that, we are running slightly ahead of time, so you've got 2 extra minutes for your coffee break. Thank you to all the partners. Thank you for being in the room. In the seats again to start directly at 11:10, so you can have a nice lunch break. Thank you very much.